Hello and welcome to Still Behind the Bench. My name is Adam, and on this channel I'll attempt to describe the science behind distilling spirits in a more technical way. Hopefully it'll whet your appetite to learn more and teach you enough so that you're more self-sufficient. So for this video I'm going to talk about why do some liquors burn while others do not. And by that I mean when you drink them. So let's get started. Okay, so why do some spirits burn and others don't? The question was originally asked on Reddit in the distilling subreddit. Their question was actually, why do low shelf spirits burn and top shelf spirits not as much? So I'm sort of going to go through what I said in that comment, but I'm going to add more because I didn't want to make that comment too long. So first you need to find out why liquor burns, and liquor burns for a few reasons that I already know about. But in researching this video, it turns out that things were vastly more complex than I ever thought they would be. And I don't have a single answer for why alcohol burns. In fact, I'm more going to be talking about a whole bunch of possible reasons why they burn and why you may find certain properties in certain spirits. I'll start with a quick high-level biology lesson about sensory receptors, since that's one of the way it all starts. So, of course, you start off with the brain. The brain is connected to the spinal cord. And then at each vertebrae, you have nerve roots that come out. Those nerve roots then branch off into what are called sensory nerves. And then the sensory nerves are connected to special cells called sensory neurons. So in these sensory neurons, which is just sort of a cell with a nerve sticking into it, you have a cell membrane. And poking through the cell membrane, you have what are called ion channels. So these ion channels act as gates letting ions in and out, like calcium, sodium, or potassium, based on certain stimuli. So an example of a sensory receptor, you have a lot of them in your body. They're called TRPs, which stands for transient receptor potential. This is specifically speaking about one of these ion channels, but I'm just going to talk about this entire thing as if it's called the TRP sensory receptor. A specific receptor in this case is called the TRPV1. The V stands for vanilloid, and then the 1 just because it was the first one that they were trying to figure out how it worked. This receptor is the main receptor in your body that detects heat. So you drink, say, hot coffee, tea, hot chocolate, and it's above a certain temperature, this receptor will notify your brain. That threshold temperature is 42 degrees Celsius or 108 degrees Fahrenheit. You hit this temperature, this gate opens and these ions start flooding in. The neuron will essentially fire like a camera flash, telling your brain that there's something hot in your mouth. The hotter it is above this temperature, the more your calcium is going to be let in, and the more it's going to tell your brain that it's very hot or painfully hot. Because this receptor not only detects heat, it is also a pain receptor when you hit certain thresholds. There are other receptors involved, and I'm going to talk about those other two later, but the rest of them, other receptors, are sort of beyond this video. So again, looking at the TRPV1 receptor, we know it detects heat, but it can also be triggered by a bunch of other compounds. I'll put a list up, but also name them. Capsaicin, which is a vanilloid. Everyone knows capsaicin from jalapeno peppers, ghost peppers, Carolina Reaper peppers. All those really hot peppers have a lot of capsaicin in them. Allicin from garlic can also trigger it. A compound called allyl isothiocyanate, which is found in mustard, radish, horseradish, and wasabi. Gingerols, which are found in ginger. Piperines, which are found in black or white pepper. Certain cannabis compounds can trigger it. Certain phenols like eugenol and guaiacol. Aldehydes like cinnamaldehyde, which is found in cinnamon. Low pH values below 5.9. Compounds that are acidic, like, if you eat too many salt and vinegar potato chips, you will get a burning sensation in your on your tongue and in your mouth. Eat any of these and your brain suddenly thinks there's something hot or pain-inducing in your mouth based on how much you eat. The TRPV1 is not the only receptor at play here. There are actually two other receptors that I'm going to talk about. One is called TRPA1. The A stands for ankyrin, which is a special type of protein that I don't know anything about other than to know that it's special. This TRPA1 is similar in how it's triggered, except it detects some different things, and more importantly, the response your brain gets from this receptor and tells you or notifies you is different. This receptor is the main pain receptor in humans. So when it's triggered, you feel pain. And an interesting side note is that this receptor in snakes is their heat detector. So if you've ever read anything about pit vipers, you may learn that they have these pits on their face, and the pit is filled with sensory receptors, and it turns out it's this sensory receptor, the one that causes us pain, lets them detect mice running around from their body. But in humans, this receptor can also be triggered by gingerol from ginger, cannabis compounds, cinnamaldehyde, eugenol, an aldehyde called pyruvaldehyde, and acetaldehyde. It can also be triggered by low pH values, so acidic compounds, and high pH values, basic compounds. Ethanol doesn't affect this one though. The third ion channel or sensory receptor that probably plays a role is called the ASIC, which stands for acid sensing ion channel. It's also a pain receptor. It just senses acids, and then you feel pain. The level of pain is based on the concentration of the acid. So let's talk about what happens when you take a sip of alcohol. Okay, so you take your first sip of an alcohol. Let's say it's your first time or it's been a while since you've had alcohol. On the more chemical side of things, ethanol is hygroscopic. That means it likes moisture. So it's going to absorb moisture from any permeable membrane that it touches. Essentially all the flesh in your mouth and your throat is a permeable membrane. That's going to cause irritation as ethanol draws water out of those membranes, dehydrating them, right? Irritation and inflammation. If you saw the osmosis video, you may remember the electron microscope photos I showed of the yeast cells collapsing due to the high ethanol concentration because water was being pulled out of them. A similar thing happens to the cells lining your mouth and throat. It's also why when you start drinking, your mouth starts to increase saliva production. So at the same time as this ethanol is pulling moisture out of your mouth, it's acting on this TRPV1 receptor. Now, it doesn't trigger it. Earlier on, I talked about how this gets triggered at 42 degrees Celsius or 108 degrees Fahrenheit. Well, what the ethanol does is it lowers that threshold temperature. It lowers it down to 34 degrees Celsius, 93 degrees Fahrenheit. That's quite a lot. And some of you may already realized your body is at a higher temperature than this. So now your core body temperature at 37 degrees Celsius or 99 degrees Fahrenheit, which is typically the temperature in your mouth, it's going to start causing your body, causing these sensory receptors, to think that your body is burning itself. On top of this, most alcoholic beverages are also acidic, which can trigger this TRPV1 as well as the TRPA1 and the ASIC. And most alcoholic beverages are acidic, right? And aged beverages, it turns out that they get more acidic as they get older. This lowering in threshold temperature is temporary though, as anyone knows that has had spirits before. Usually, even if it's your first time, the burn goes away within seconds to minutes at most. That said, there are also some compounds that can inhibit the triggering of the receptor in the first place. Some of the compounds I already listed as triggers can also desensitize the receptors. Desensitization comes about when the receptor is triggered so often at too high of a level that the receptor just stops reacting, or the brain just starts ignoring it and you no longer feel that sense from that sensor. It also turns out that ethanol, while not desensitizing receptors itself, can lead to faster desensitizing by other compounds. Compounds like eugenol and guaiacol, commonly found in whiskeys, are desensitizers. In fact, eugenol, which was originally extracted from cloves, used to be used in dentistry for numbing areas in your mouth. There's a compound called naringenin, which is found in lemon peels, and a compound called quercetin, which is found in oak, that are also inhibitors. And some fatty acids like linoleic and oleic acid are also partial inhibitors. You probably already know that if you continually eat meals with capsaicin, you become desensitized to that heat. You know, just talk to Sean, the host of the Hot Ones on the First We Feast YouTube channel. I don't understand how he can eat some of those hot sauces and not even react to them. It's insane. So those are some of the compounds that and ways that these things interact with your body biologically. I'm going to get into some of the compounds that don't necessarily interact with you biologically, but it's more of a chemical reaction. So we have these compounds that are chemically or more chemically active than they are biologically active. Things like acetone, methyl ketone, ethyl acetate, which we know gives a fruity taste in spirits, but concentration gets high enough and it can start causing problems. And acetaldehyde, which I've already mentioned can trigger the TRPA1. It will also act chemically when you ingest it. So all these compounds are great solvents, like really great. And because of that, they can cause significant inflammation and irritation when they're in your mouth and going down your throat. While the concentrations are never going to be all that high, it's enough that it can play its role. And these are typically found in the heads. So the only reason you're going to be finding them in your spirits is because somebody was making bad cuts. And it's going to be more often happening with low shelf spirits because they're trying to increase, or I should say, because they may be trying to increase the amount of product that they can sell. So you take a little bit more of the heads. Now we can look at some of the compounds that show up as the result of aging. So for spirits that are aged on wood, referencing a study that I've linked down to in the description, the study did tests on 6 different proofs of spirits aged in oak casks over 12 years. They found that the older the spirit is, so the higher the aging, or the longer the amount of aging, the higher the concentration of acids, esters, fusel oils, aldehydes, furfurols, tannins, phenols, phenolic acids, and phenolic aldehydes. I imagine it was probably even higher, more compounds than that, but maybe they didn't know to test for them or how to test for them, because it's a pretty old study. But we know from what I've said previously, that quite a few of these compounds that fall into these classes can all trigger the sensory receptors. Acids will trigger all 3 of them, TRPV1, TRPA1, and ASIC. Esters, like ethyl acetate, will be acting like a solvent, right? A lot of esters will be acting like solvents, and so they can just cause inflammation on their own. Fusel oils are higher alcohols like isoamyl alcohol. Aldehydes like acetaldehyde. Furfurols, they aren't found in all that great of a concentration. I don't know much about furfurols. Tannins really aren't going to do anything, but phenols like guaiacol and vanillin can cause problems. We know that guaiacol is a trigger for TRPV1 and TRPA1, but it's also an inhibitor. So maybe high concentrations of guaiacol in spirits that are aged older is helping play a role in top shelf spirits not burning as much, right? Maybe it's acting as an inhibitor. Certain phenolic acids will cause both irritation and trigger those receptors. And then we get phenolic aldehydes like cinnamaldehyde, which can trigger the TRPA1, I believe it is. So let's rehash what I've gone over so far. So to rehash it, ethanol is going to drop the temperature threshold, right? From 42 Celsius, 108 degrees Fahrenheit, to 34 degrees Celsius, 93 degrees Fahrenheit. Those listed compounds that I've talked about before can trigger the TRPV1 receptor to sense heat or pain. Lots of those same compounds can also trigger the TRPA1 receptor, so you just feel pain. Then on top of that, some of those compounds, like the acids, can trigger the ASIC receptors, as well as these others. Then on top of that, some of those compounds can trigger these receptors so fully and so often that they can desensitize receptors. So these receptors stop communicating with the brain. And we know that although ethanol doesn't trigger the receptors, it can increase the rate of desensitization. Then we just have regular chemical irritation and inflammation, and osmotic-based issues where certain compounds are pulling moisture out of the membranes in your mouth and throat. So what is it that causes the burn that makes you exasperate the word smooth? Turns out it's a lot of things, and you really can't just point to one. I haven't had a drink in a while. It's been a few weeks, so I tried some out, just a cheap bottle of Jack Daniels, to see if I could get that burn. And paying very close attention to the sensation itself, I realized that it isn't just or even mostly a hot burning sensation. And while there is heat sensation there, I find it is more of a prickly stinging sensation than heat, at least for me. To get past that kind of experience, you just need more experience. Don't become an alcoholic, but just like with hot peppers, the more you drink, the less pronounced that effect will be. I try to put in hot sauces in pretty much almost everything I eat. And while I don't while I still feel the heat, it's nowhere near as bad as when I originally started doing it. Talking to people who drink regularly, more regularly than me, they still get a bit of burn, but it's nowhere near what it used to be. I don't think you can completely get away with it. I mean, if you drink a lot of high alcohol concentration spirits and then you go drink a beer or a wine, you may not notice the alcohol at all, may not feel any sort of burn. I mean, I don't think you'd feel a burn in the first place. I don't recall ever feeling a burn from beer or wine, but some people, they might get it. But to get specifically back to the whole low shelf versus high shelf thing, I imagine the real difference is in the chemical or I should say long term, I think the real difference is in the chemical irritation. Essentially, how bad the cuts, how deep into the heads and tails they go when making the cuts. I also think that the amount of aging that happens will play a big role. Probably depend on what wood they're aging with as well. The more inhibitors you get, I think will lower the amount of burning that you get. And probably quite importantly is whether or not they include additives. Things like sugar alcohols. I'm not quite sure why sugar alcohols or sugar itself seems to smooth out rough beverages, but it does. I'm actually researching it to do it for another video when I actually get an answer, but I'm slowly coming to the conclusion that I don't think anybody has researched that specific topic, or at least not put out anything public about why sugar alcohols or sugars can perceptibly smooth out a spirit. This leads me to another recently researched property of spirits. It's somewhat relatively new, and it's called structurability. Okay, so structurability. I've posted some DOIs for some studies, as well as an interesting article that touches on it down in the description. It turns out that at certain water-ethanol ratios, hydrates form. So what's a hydrate? A hydrate is just when a molecule bonds with water. I'll go into a bit more about what a hydrate is. So if you've ever been shopping for certain compounds, say you want to make up your own nutrient solution or something, or your own nutrient powder, you may have seen certain things end with words like monohydrate or pentahydrate or decahydrate. All that means is there are that many water molecules attached to one molecule of whatever's in there. So if it said citric acid pentahydrate, that means there are 5 H2O molecules attached to every citric acid molecule. And that's all it really is. So why does this matter? Well, if water ethanol is in this hydrate form, it means the ethanol is surrounded by water molecules. So it is entirely possible that the caged ethanol molecules never will interact with the TRPV1 receptor. They'll never lower the temperature threshold. It also turns out that a higher concentration of certain phenolics, acids, and salts can not only cause stronger bonding with these hydrates, so between the ethanol and the hydrates, but it can cause more hydrates to be created in the first. So phenolics and acids will come from aging, or they can come from fermenting and distilling, just fermenting and distilling. Salts are typically going to be coming from the water you use to dilute. So if you use tap water or a mineral water, it's entirely possible that you have the right salts in there. So they gave some examples in one of the studies, and they were magnesium chloride, which will be found in hard tap water, magnesium sulfate, which is Epsom salt, which can also be found in hard water. So this whole structurability thing is more, I'd say, hypothetical right now than it is. I don't even think it has gotten to the point of a scientific theory. It's still a hypothesis. Not my hypothesis, other people's hypothesis. Yeah, it's something that they're going to be researching. So I figured I'd point it out because this could be playing a significant role in how we perceive alcohol when we drink it. Another thing I want to talk about that I noticed is that if you aren't told anything about the spirit before you drink it, but you automatically associate a higher viscosity spirit with a higher quality, what psychological impact does that have on you and the burn that you perceive? Lastly, we should also be aware that there is simply going to be a bias, even unconsciously. It's inherent to being told something is high quality, top shelf. It's entirely possible that you can trick your mind into not perceiving the amount of burn that would otherwise be present simply because you're being told this beverage is high quality, it's smooth, it's silky, it has great mouthfeel, it's expensive. There are lots of videos on YouTube tricking people about thinking product X is high quality when it's actually low quality product Y. So I know I probably didn't give the most satisfactory answer to the question. I feel like I didn't give a satisfactory answer, but I don't think there is a very satisfactory answer to this question in the first place, or any of the other questions I've asked near the end of this video, at least not yet. So to essentially wrap everything all up, it essentially comes down to ethanol tricking your body into thinking it's burning itself, ethanol and congeners causing inflammation, congeners causing sensory receptors to fire, congeners attempting to prevent sensory receptors from firing, experience in drinking alcohol, which leads to desensitization, and finally just some other possible effects, structurability, and the potential psychological effects like bias. That's essentially what the difference is between low shelf and high shelf. It's a lot of different answers. And if I find out more, I will do a follow-up video. Before I end the video though, I would like to thank my Patreons. You guys really do help me out. And that's it for this video on why some liquors burn and others do not, sort of. I hope you learned something. Please click like and subscribe if you want to see more, and have a great week.